Now, this point you are, I mean, the bonding you are already familiar with ionic bonding. You know that it is composed of both metallic and non-metallic elements, and normally situated at the extreme ends of the periodic table. When the metal loses up their electrons to become a positive ion, and uh, the non-metal, or uh, the element which is situated to the extreme right of that periodic table, it normally uh, gathers up that electron and become a negatively charged ion. They eventually achieve the stable electronic configuration, and this is the case for sodium and chlorine to form sodium chloride bond. And this is a bond which is based on the coulombs, or the attractive positive negative ions, by virtue of the net electron charge. So they're having stable electronic configuration by losing up an electron and by taking up an electron. And this bonding essentially have an energy that ranges from 6 to 1500 kilojoules per volt per mole, or 3 to 8 electron volts per atom. This is the energy that is being generated by the ionic bonding. Probably this would be a new information for you, but the rest of the thing are very clear to you. Similarly, the covalent bonding, you have sharing of electrons between adjacent atoms. That means two atoms are covalently bonded, will contribute at least one electron to the bond, and the shared electrons may be cherished by both the atoms. For example, the case of methane CH4, where there are four hydrogen atoms, each sharing an electron with the carbon. The carbon has four valence electrons. So each of the hydrogen is sharing an electron with carbon, and eventually the structure that you would have that the carbon would have 8 electrons in the valence shell, and hydrogen would have 2 electrons in the valence shell, and thus they would both achieve the stable configuration. But you should remember that the important thing, covalent bond is a directional bond. It is between specific atoms and may exist only in the direction between one atom and the another. So this is the direction of the bond. If I ignore these three bonds over here, this is a directional bond that is taking place between the two adjacent atoms. uh, the third kind of bonding is the metallic bonding. And the final primary bonding in metals and the alloys. And this is very simple to understand. Metals have one, two, or at most three valence electrons, and these valence electrons are not restricted to any particular atom in the solid, and they are more or less drifting through the entire material. So you refer to this drifting of electrons through the material as the electronic cloud, or the sea of electrons. Thereby, the core, which is that of non-valence electron, is basically having a net positive charge, which is equal in magnitude to the valence electrons, total valence electrons charge per atom. Therefore, the metals are known as good for their electric and heat conduction, and the conductors are basically these free electrons. So you have these cores which are positively charged, and the electron sea of electronic clouds that is there. Uh, I hope it is clear so far.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
All right. So if it is clear, let's move on towards the secondary bonding, or which is known as the van der Waals force bonding. So secondary van der Waals or physical bonds are weak in comparison to the primary chemical ones. Bonding energies typically range from 10 kilojoules per mole, or zero point 0.1 electron per atom. This is very weak sort of bonding. And bonding forces, they arise from atomic or molecular dipoles. Uh, in essence, an electric dipole exists whenever there is separation of positive and negative charged portions of atoms or molecules. This is known to you. Uh, the bonding that exists is basically due to the Coulombic attraction between the positive and negative dipoles that are created, or the positive or negative regions that are created adjacent to one another. So if within the atom you have positive and negative regions created, that would essentially create a positive and negative region in a neighboring atom, and thereby there would be temporary, or there would be van der Waal or secondary bonding between the adjacent molecules or atoms. Now there could be two kinds of it. One is fluctuating induced dipole bonds. So atoms, they're experiencing constant vibrational motion that can cause uh, instantaneous or short-lived distortions of electrical symmetry for some of the molecules. That means if you have a stable atom where the nucleus is situated within the center, due to the vibrational motion, what would happen would be that, for an instance, the nucleus may get uh, cornered to one end, and thereby creating a positive charge at one end, and the electron cloud gets distorted to the other side, thereby creating a net negative charge on the other end. This is an instantaneous uh, uh, phenomena that takes place within the uh, atomic structure due to vibrational motion. One of these dipoles can in turn produce a displacement of electron distribution of an adjacent molecule or atom, which induces the second one also to become a dipole. So this momentarily process, or this process that occurs for certain uh, period of time, in turns create another dipole to the in the neighboring atom, or neighboring atom, thereby having a van der Waal force or van der Waal bonding being created between the two atoms. These again are temporary and they fluctuate with time. So this is important aspect of the fluctuating induced dipole moments. Polar molecule induced dipole bonds, they are permanent dipole moments that exist in some molecules by virtue of an asymmetrical arrangement of positively and negatively charged regions. Such as molecules are termed as polar molecules. You must have heard about them. Hydrogen chloride is a molecule which has having a permanent dipole moment that arises from net positive and net negative charges that are respectively associated with hydrogen and chlorine ions. And this basically in turn creates this permanent dipole, creates van der Waal forces that exist between adjacent polar molecules. Now, you should remember that the van der Waal forces, or the secondary bonding energies for polar molecules having permanent dipoles, they are significantly greater than for bonds which include bonds involving induced dipoles. That means the fluctuating dipoles, this sort of bonding would have higher energy as compared to the fluctuating induced dipole moments. Is this clear to you?
Yes sir. So it means that जो ionic bonds बनाते हैं वो भी polar molecule induced dipole bonds बनाते हैं. Because usually ionic
Ionic
bond may fluctuate.
Ionic में
And
essentially there is a sodium ion that is already positively charged. Yes, that is Coulombic attraction that is taking place. Their energy is much more higher. इसमें bond जो है basically आप कह सकते हैं, क्योंकि इसमें फिजिकल इलेक्ट्रॉन गिव अवे नहीं हुआ होता. ऑलराइट, इट्स स्टिल the
so
electronic
in a
configuration
positive और एक negative end बन रहा है.
जी सॉरी.
सिर्फ वो इलेक्ट्रॉन डोनेट करने की वजह से एक एंड पॉजिटिव हो जाता है और दूसरा एंड नेगेटिव हो जाता है.
नेगेटिव
तो
हो
वो
जाता है, लेकिन वो फिजिकली डोनेट हो चुके होते हैं. इसमें शेयरिंग पे चल रही है चीज फिलहाल. क्लियर? Although there is a dipole movement, that permanent dipole that has been created, but again you cannot exactly uh, uh, say that they are the same thing. All right.
Yes, sir.
फिजिकली एक चीज डिफरेंट है.
सर आपसे ये पूछना था ये जो पोलर मॉलिक्यूल इंड्यूस्ड डाइपोल बनाता है सर वो तो परमानेंट नहीं होंगे वो टेम्परेरी क्यों होते हैं?
टेम्परेरी तो नहीं है, परमानेंट ही है वो.
परमानेंट ही है ना सर?
जी जी
ठीक है तो सर फिर ये जो परमानेंट डाइपोल बॉन्ड्स हैं वो
जी.
फिर मतलब क्यों ज्यादा स्ट्रॉन्ग है पोलर मॉलिक्यूल इंड्यूस्ड डाइपोल बॉन्ड्स?
वो ज्यादा स्ट्रांग नहीं है, वो जो फ्लक्चुएटिंग इंड्यूस्ड डायपोल बॉन्ड्स हैं उनसे ज्यादा स्ट्रांग है.
ठीक हो गया सर, ठीक हो गया,
ठीक हो गया.
ठीक हो गया.
All right. So now let's move on towards the classification of metals. This is the second half of this session. Probably this would be something that would not have been uh, in your knowledge beforehand. So metals basically are classified into categories of ferrous and non-ferrous materials. In the ferrous category, you have steels and cast iron. Steels are basically alloys that have primarily major portion of iron plus certain amount of carbon in it, and will represent the composition in weight percent. That means out of 100 how much is iron and how much is carbon. This is how we represent steel. The other non-ferrous categories includes copper based alloys, aluminum based, magnesium based and titanium based materials. Again, all fall in the category of metals, but you have a restriction of ferrous and non-ferrous over here. Steels, they have normally carbon less than 1.4 weight percent. That out of 100%, if iron is 98.6%, you can have a maximum of 1.4% of carbon, and you can still refer to it as steel. For cast iron, you would refer to as cast iron materials that have carbon in the range of 3 to 4.5%. The rest of it is iron itself. This is the major classification. Don't worry about the microstructure at the moment. The cast iron, they are known for having graphite in them. Why? Because there is more amount of carbon in it, so it normally forms graphite in the cast iron material. But for now, you need to understand the distribution of carbon within steels and the cast iron. Now, with specific regards to steel, steel is further classified into very specific subcategories. You refer to steels as low alloy steels and high alloy steels. For the moment, you don't worry about high alloy steels. Within the low alloy steels, based on the amount of carbon, you can refer to steel as low carbon steels, medium carbon steels, and high carbon steels. So if you have less than 0.258% of carbon, you call it low carbon. If you have in the range of 0.25 to 0.68%, you call it medium carbon. And if you have 0.6 to 1.48% of carbon in a steel, you refer to it as high carbon steel. Within these three categories, low, medium, and high carbon, there are further still two categories. One is known as plain carbon steel, in which there is no other addition. The additions are not there. There is no addition to it. Steel is made up of iron plus carbon. So other than iron plus carbon, there is no addition in plain carbon steel. So each of the three, low carbon, medium carbon, high carbon, they have a plain category in which there is no additions to the original steel. Then there is another category which all three of them uh, cherishes, the high strength low alloy steel, which is known as HSLA steel, which is associated with low carbon steels. They have chromium, vanadium, molybdenum, and nickel additions to it. Uh, then medium carbon steels, they have another category which is known as heat treatable steels. They have chromium, nickel, molybdenum additions. Obviously, the percentages differ. And the high carbon steel, they have a name, a category, subcategory which is known as tool steels. Again, they have chromium, palladium, tungsten, molybdenum added to these as an addition. If you refer to the name of these materials, Plain carbon steel could be 1010, 1040, 1095. How do you represent these names? We'll come to see in the next class. How do we, next slide. How do we identify the names? The high strength low alloy steels is represented by 4310 series or 4340 series or 4190 series. You don't need to worry about the names at the moment. You just need to worry about how the different classes are being categorized. And then comes the high alloy category of steel. The most famous one is the austenitic stainless steel. And the austenitic stainless steel, it has high percentage of alloying elements. 18%, 8%, 11%, high additions of alloying element. The alloying element are normally chromium, nickel, molybdenum. There are also others, but these are the known ones. And the austenitic stainless steel, one of the famous austenitic stainless steel, has a name of 304. SS304 is a common austenitic stainless steel. And when we come to the properties, we are discussing three properties: hardenability, what is the potential of getting or converting this material into high hardness, or how high you can have the hardness of this material, tensile strength, and elongation, the ductility. So if you see
सर एक क्वेश्चन है
zero,
सर
जी पूछिए।
सर ये हाई अलॉय की ये क्लासिफिकेशन है ही नहीं, या हम इसको यहाँ डिस्कस नहीं कर रहे, हमारे साथ कंसर्न नहीं है इसका।
है, और हमने डिस्कस भी किया हाई एलॉय में। एक एक हाई एलॉय जो मैंने आपसे डिस्कस किया वो ऑस्टेनेटिक स्टेनलेस स्टील है, जिसमें परसेंटेज ऑफ अलॉइंग एलिमेंट्स जो बाकी अलॉइंग एलिमेंट्स जो हमने डिस्कस किए उनसे बहुत ज़्यादा होती है। हाई अलॉय का मतलब ये होता है कि द परसेंटेज ऑफ अलॉइंग एलिमेंट इज वेरी वेरी हाई और रिलेटिवली वेरी हाई। ठीक है, इसमें होगा, फर्ज करने क्रोमियम होगा, इसमें बहुत हुआ क्रोमियम, टूल स्टील में कोई एक टूल स्टील का कैटेगरी होगी जिसमें लेट से क्रोमियम इज 4%, ऑस्टेनेट स्टेनलेस स्टील में क्रोमियम कुड बी 18%. All right.
Right.
So this is high. When I say high alloy, that means the percentage of additions is very high. All right. This is separate category. When you refer to tool steel is a category of steels. They have carbon in this range, and then they have alloying elements along with it. You would have different tool steels, D2, D1, and there are other W2. There are different tool steels that are there, so you don't need to worry. But the category of that they would be falling into would be high carbon steels, and within high carbon steels you'll have the category of tool steels. Clear enough?
Yes sir.
सर ये जो आपने क्रोमियम का बताया सर, ये विद इन कार्बन के परसेंटेज में होगा या फिर सेपरेटली होगा उस मेटल के अंदर?
जब आप कहते हैं ना 18%, so percent is out of what?
सर होल सब्सटेंस।
जी होल सब्सटेंस। जब ये कार्बन भी बता रहे हैं 1.4, तो दिस इज 1.4 ऑफ द होल 100%। ठीक है,
ठीक है सर, ठीक है सर।
Now, hardenability, tensile strength, elongation. Negative sign means lowest, 0 means a little higher, plus means a little more higher, plus means more, and plus means much higher. So if you look at the trend, you would see that the strength and cost is increasing in this direction as you move from low carbon to medium carbon to high carbon to high alloy. Your strength is increasing, your cost is increasing, and ductility is essentially decreasing. Except for this high alloy, you would see the ductility is decreasing. Now just look at the major applications of these materials. Plain carbon auto structure sheet, high strength low elastries, bridges, towers, pressure vessels. Medium carbon plain steels, crankshafts, bolts, hammers, blades. Medium carbon heat treatable steels, pistons, gears, normally used for wear application. High carbon steel, wear applications. Tool steels, they are used for drills, saws, manufacturing dies, they are made up of tool steels. Austenitic stainless steel, high temperature applications, turbines, furnaces. applications that require high corrosion resistance, stainless steel is being used. So this is a generic distribution of steels that you should be aware of. Then comes the naming category. How do you name steels? The nomenclature, American Iron and Steel Institute, AISI nomenclature. 10 is for plain carbon steels. The next two digits, plain carbon steels only have iron plus carbon. So if you have to identify plain, if you have to represent a plain carbon steel, you'll represent by 10, and there would be two digits next to it. The next two digits would represent the percentage of carbon. For example, it means the percentage of carbon is 0.60, and if I see 0.60 falls in high carbon category. Similarly, 11XX means plain carbon steels resulfurized for machinability. You don't need to worry about what is resulfurized, but this is a category that makes machinability of materials easier. 15XX series, a series which has at least manganese from 10 to 20%. 40XX series, molybdenum having 0.2 to 0.3%. 43XX series, which has nickel, chromium, and molybdenum in the same range. XX in all the 5 categories, XX basically represents the percentage of carbon. Stainless steel, as I have said, it contains chromium greater than 11%, so it's a high alloy steel. You don't need to worry about it. So the nomenclature is clear to you?
यस सर, मगर सर ये बताएं कि मशीनेबिलिटी क्या चीज होती है?
Machinability is when you are removing material from the material. For example, एक shaft को आपने कम डाई का करना है और आपने उसके ऊपर से मटेरियल उतारना है, तो you have to machine it. Alright, आपने मैन्युफैक्चरिंग प्रोसेसेस का कोर्स पढ़ा है?
नहीं सर।
यस सर, ये पढ़ा सर।
सर हमने
Manufacturing
बेसिकली
जी सॉरी
नथिंग सर, आप प्लीज कंटिन्यू करें।
Alright, machinability means that it becomes easier to machine it. Sulfur की presence में normally material brittle हो जाता है. Again, you have to treat it, resulfurize it, so that it becomes easier to machine. Anyways, you don't need to worry about it, but you need to understand 10 and 11 is a different series. Clear?
जी सर।
सर एक क्वेश्चन था।
जी पूछिए।
सर ये आपने 1060 स्टील का बताया, तो इसमें 0.60% कार्बन की है, लेकिन आपने उधर हाई में बताया था कि 1.2% तक जा सकती है, तो सर वो किस तरह हम डिटरमिन करेंगे?
1.2% तक ऐसे कहाँ पे बताया 1.2 तक?
सर 1.4 ये सर हाई कार्बन में 1.4 आई थिंक साहब ने लिखी है ना।
आप ये कह रहे हैं 10 और
सर XX की जगह जब हम 1.2 लिखेंगे तो वो तो 0.12 सीम्स टू बी 0.12 होगा ना।
हाँ जी।
लेकिन सर 1.2% किस तरह सर कैलकुलेट होगी?
क्या मतलब आप क्या कह रहे हैं?
1.4%। यस सर 1.4 है ना सर? 1014 लिखें
जी।
तो सर इसका क्या मतलब है कि ये 0.14% है ना?
ये 0.14% है नॉर्मली, और
लेकिन सर वहां पर जो 1.4% हाई कार्बन की हाई
जी मैं आपको बता देता हूँ। नॉर्मली आप जब कार्बन स्टील्स को स्पेसिफाई करते हैं ना, तो 1.4%, इफ यू गो बैक टू दिस स्लाइड, लेट मी गो बैक, ये लिखा हुआ ये है कि स्टील्स नॉर्मली ना लेस देन 1.4 वेट परसेंट कार्बन के साथ स्टील्स कैटेगराइज होते हैं। लेकिन इफ यू go into the market and if you ask for a steel having 1.4 weight percent of carbon, you would not normally find it. हायर कार्बन जो है ना, वो इतना हाई कार्बन का स्टील आपको नॉर्मली मिलता नहीं है। वजह ये है कि नॉर्मली आपको जैसे जैसे कार्बन आप डालते जाएंगे ना, इफ यू सी ओवर हियर, जैसे जैसे आपका कार्बन इंक्रीज होगा ना, कॉस्ट आपकी इंक्रीज होती जाएगी और उसका यूजेज इतना ज़्यादा नहीं होता। So normally you would not find a material having this much weight percent of carbon within the market. लेकिन आपका सवाल ये जायज़ है कि if you have 1.4 weight percent of carbon, how would you express the name in terms of plain carbon steel? I would have to check it up because I have not looked it into as yet. I have not used a material having that much amount of carbon, but I'll look it up and I'll get back to you. All right.
Okay, sir. Okay.
All right. Now, the last category is the category of non-ferrous alloys. In non-ferrous alloys, you have copper alloys. The most common is is the brass, which is uh, which is an alloy of copper and zinc, where zinc is basically the low alloying element in it. And the general purpose for brass based alloys is that uh, it is corrosion resistance. It's more corrosion resistant. And then you have a category of bronze. What is the difference between brass and bronze, by the way?
Sir, bronze.
अलॉयज हैं सर दोनों लेकिन मुख्तलिफ जो हैं मेटल से बने हुए
जी
There are different impurities.
Yes, in bronze you essentially have tin, aluminum, silicon, and nickel as the impurities, and they are normally used for landing gears. Copper beryllium, it's a special category of alloy which is precipitation hardened for strength. What is precipitation hardening? We'll look into it when we'll go towards the hardening mechanisms. So you don't need to worry about it at the moment. And then comes the titanium alloys, titanium based alloys, aluminum based alloys, magnesium based alloys. If you see the density of these materials, 4.5 grams per centimeter cube, 2.7 grams, 1.7 grams per cent, they are very lightweight. So they are normally used for aerospace applications. All right.
Yes, sir.
Yeah,
Sir,
yes,
can you
sir.
please repeat this point?
Sorry,
Can you please repeat
सर
this
इसे
point?
रिपीट कर दें
कौन सा point repeat कर दूं?
सर ये एरोस्पेस एप्लीकेशन आपने क्या बोला एरोस्पेस
Yes,
एप्लीकेशन
sir.
वाला पॉइंट
Normally, if you compare the density of titanium alloy with aluminum and magnesium alloy, you would see that densities are very low, 2.7, 4.5, 1.7. So these alloys are normally used for aerospace applications that require good strength to weight ratio. All right.
ठीक है सर
And then you have refractory metals. They have niobium, molybdenum, tungsten, tantalum. They are basically refractory materials. They have high melting temperature, so they are used as refractories in steel industry or in other industries. And then you have noble metals such as silver, gold, platinum. They are oxidation and corrosion resistance. They have specific applications, and they are expensive as they have a noble characteristics to them. So
So why they are
this is
classified as
sorry.
so why are they classified as noble?
Because they are corrosion resistance. If you place them in open environment, obviously I'll not be able to explain it as good as uh, I mean, at the moment, you since you're not familiar with the corrosion phenomena, you'll not be able to understand it at that much. But if you place a piece of steel in an open environment and a piece of gold in an open environment, what do you expect? Which of them would corrode more?
Steel.
Obviously. So they are noble because of their characteristics that they can maintain their identity for a very long period of time. Clear?
Yes, sir.
सर एक सवाल है सर
जी
सर ये आपने बताया जैसे एप्लीकेशन बताई है जैसे टाइटेनियम के एल्युमिनियम की, अगर हम इसको
जी
किसी चीज में यूज करते हैं, सपोज हमने एरोस्पेस में यूज किया है, तो इसके अंदर
जी
एक करेक्टरिस्टिक तो होगी कि इसकी डेंसिटी कम है, स्ट्रेंथ टू वेट रेशियो है, लेकिन उसके साथ इसके अंदर दूसरा एक फ्लॉ भी हो जाएगा, तो फिर वो हम
क्या?
ओवरकम कैसे करते हैं इस तरह?
कौन सा फ्लॉ?
सर जैसे ये टाइटेनियम जो है वो रिएक्टिव है हाई टेम्परेचर पे,
हाँ
तो अब सर जब ये इसका मेटल हम यूज करेंगे, टाइटेनियम यूज करेंगे, तो ये रिएक्टिव नहीं हो जाएगा जब
नॉर्मली
टेम्परेचर हाई
नॉर्मली
होगा?
नॉर्मली टाइटेनियम जो है वो प्योर फॉर्म में यूज नहीं किया जाता। नॉर्मली टाइटेनियम एलॉयज यूज किए जाते हैं। देयर मेनी एलॉयज बेस्ड ऑन टाइटेनियम। आई एम जस्ट गिविंग यू एन एग्जांपल कि बेस मटेरियल आपका टाइटेनियम है। ऑलराइट
सही है, सही है सर।
ऑलराइट, एनी अदर क्वेश्चन?